Okay, so now let's look at the scattering states for this problem. For example, resonances, they are not really things that you can just solve an eigenvalue equation of, because they are not eigenstates. They don't correspond to a given eigenvalue. So practically, there is no way. It will be quite complicated to look for a resonances just by solving the Schrödinger equation. But scattering solutions just allow you to determine the resonances. Now we need to solve this. Okay, so it's not, well, all states are in a sense scattering states, because if lambda is finite, there is no bound states. There is no real bound states. So let's solve our equation. This is our equation. Epsilon now can take any values, but of course it has to be positive. There is no negative energy solution. And we solve for x is less than 1, u is equal to a times sine kx. For x is larger than 1, it just looks like the previous case, u is equal to, this time we have the oscillating solutions outside. And the oscillating solutions, a time, we can just write as b times e to the power I kx plus c times e to the power minus I kx minus 1. And they are the same k, because the energy inside and the energy outside, they are the same. The potential is 0, both inside and outside. And to determine B and C, we just need to match the two solutions, the inside solution and the outside solution. The inside, the matching conditions are, the wave function has to be continuous at x is equal to 1, which gives us a sine k should be equal to b plus c, and the derivative should be continuous, a k cosine k. Well, the derivative is not continuous. Sorry, you are right. We don't have the continuity of the derivative. So this is one condition we have. The derivative will be discontinuous, and to obtain the discontinuity, just take this equation. And integrate both sides over x from 1 minus to 1 plus. Just from the left of x is equal to 1 to the right of x is equal to 1. So we have minus du by dx, evaluate that x is equal to 1 plus, minus du by dx, evaluate that x is equal to 1 minus. And the Dirac delta tells me that the integral of the Dirac delta is lambda tilde times u at 1. And this should be equal to 0, because u is finite, epsilon is finite. If you integrate a finite function over an interval of 0 length, you get 0. So if you just, we already know the inside and the outside solutions. You can just take the derivatives, put it here, and let's see what we get is minus, for x is equal to 1 plus, the derivative is ikb minus ikc. This is the value of the derivative at x is equal to 1 plus, minus the derivative at x is equal to 1 minus is ak sine k plus lambda tilde. Well, u equal to 1, we can just use the inside solution or the outside solution. It doesn't really matter, because both of them are continuous. They are continuous. They are equal. So, yes, cosine k. Lambda times sine k. This should be equal to 0. So let us just rearrange it a bit. A lambda tilde times a sine k. So we have minus I k b minus c plus a k cosine k plus lambda tilde a sine k This should be equal to 0. Or b minus c, this is equal to 1 over ik, a over ik, k cosine k plus lambda tilde sine k. So this is what b minus c should be. We also had found b plus c here. This is b plus c. So now we can just find b and c. B should be equal to a sine k plus a over ik, k cosine k plus lambda tilde sine k, and c is equal to a sine, there is also 1 over 2, a sine k minus a over ik, k cosine k plus lambda tilde sine k, and again 1 over 2. And again, both of them, at least let's say, we can just choose a to be 0, 1. I mean, it's just normalization. And as in the previous case, b is equal to c star. It has to be b is equal to c star. Because if you look at the solution, the generally solution we have, this one, we are just sending in a wave that is c, and then it interacts with the potential and then comes out. The only solution at the zero potential region is e to power plus or minus ik. That cannot change. L is conserved, and this is for L is equal to 0. We cannot have other L solutions, and the only option is that they differ by a phase. So that tells us that B and C should be conjugates of each other. And again, the phase that the ingoing wave acquires, the relative phase that the outgoing wave acquires relative to the ingoing phase. Okay, this is the outgoing one, this is the ingoing one. So the phase is b times e to power minus. Now this is outgoing. This is ingoing. So the outgoing wave has a relative phase that is b times e to power minus 2ik over c. This is the relative phase. This is our e to power 2I delta. L is equal to 0. Now this time we cannot just go to K, analytically continue K to I kappa, because energy has to be positive. There is no negative energy solution. The potential is positive, the kinetic energy is positive, so the total energy has to be positive. But let's see if there are any places in the complex K plane such that e to power 2I delta L minus 1 over 2I diverges. You see, delta L for real K, delta L is a real number, and since delta L is a real number, e to power 2I delta L is a complex number with unit norm, so this is finite. This number is finite for real K. It has no divergences for real K. But for complex K, it might have divergences. So that is what we will be looking for. Because for complex K, delta L is no longer a complex number. So I define this function f. If you look at this function f, it is nothing but, oops, here. This is my function f. So if you just write b is, you see, just take the sign parentheses, b is a out. In sign, you have 1 plus lambda tilde over ik, 1 plus I times lambda tilde over, lambda tilde over k. This is this factor over here, the first factor over here, this one. Alpha is lambda tilde, beta is k. So this is my e to the power 2i delta. So here I just say, okay, 1 plus, no, 1 minus. And pi, I'm just normalizing k by pi, because I know that the bound states, if lambda was infinite, the bound states happen that k is equal to n pi, integer n, multiplied with pi. But n this time, I won't let it to be, I will just let it to take any value, because there are no bound states, there are no strict bound states. K can take any value in this problem. I'm also adding an imaginary number. This is my k. I'm also adding an imaginary number to it. Now lambda tilde is nothing but our lambda tilde. So I'm just taking the absolute value. If this thing diverges, then its absolute value diverges. So that's what I'm trying to do. And also this absolute value, I ignored some factors of 2i, etc. But the absolute value squared is also nothing but my cross-section corresponding to L equal to 0. S, so-called S-wave scattering amplitude, scattering cross-section. Now this is how it looks like. For lambda tilde 1, that's some small number. You see there is a pole over here that you see. And it is located at, let's say, this is the real part of k. The real part of k is something like 0.7 here. This is the real 0.7, 0.8, somewhere in between there. And there's also the imaginary part. The imaginary part is something like 0.7. Now, if lambda was infinite, we had already seen that there has to be one bound state when n, this n over here is 1. There has to be a bound state for n is equal to 1. The real part of this one is kind of a bit shifted from n is equal to 1. N is equal to 1 is over here. So there is this lambda, which allows my particles to tunnel out of my sphere. Lambda is finite now. The finite value of that lambda causes my particles to tunnel. So if I create a state inside, which is a long-lived state inside, it has energy slightly shifted than the eigenstates I would have if lambda was infinite. And of course, I would expect this shift in the energy to disappear as lambda increases. So we can, let's test this. This is lambda. Let me increase lambda. This is 2. Now the eigenvalue is somewhere around 0.8, the real part. 3. The real part is approaching. Let me just take a larger one. 6. Now this is where the real part is somewhere close to 0.9. And also you see the imaginary part. The imaginary part is disappearing. So before it was somewhere over here. In the imaginary axis, the imaginary part was something like 0.7. Now it is 0.2. Let us even increase it further from 6 to 15. Now it is even closer. And that is where our peak is. And the value is also close to 1. Closer to 1 now. It's something like 0.95. It is getting closer and closer and narrower and narrower. This is the first, what we call the first resonance. Now, if we look at the second one, well, the second one is also very close to 2. And this is for a large value of lambda. Very close to 2, and the imaginary part is again very small. Well, if we make it the lambda to be smaller, it moves away. Let's look at the third one. So at m is equal to 3, well, this is the third one for small lambda. Again, the real part is somewhere close to 3. So k is close to 3 pi, 2.7 pi. And if we make lambda larger, so it approaches 3. The larger lambda gets, let's say, 100. Well, it's hard to see now. It's something over here. Now, of course, the thing is, this is not what we will see in the experiment. In the experiment, we cannot scan for complex wave vector. What in the experiment we will see is we will just take the absolute value squared along the real axis. This is what we will see in the experiment. 1 plus f squared. For small lambda, nothing much really. And if you remember in the complex plane picture, it was very far away from the real axis. Now, if we increase lambda, now it's approaching to the real axis, and now we have this peak in the scattering. This is basically what we observe in experiments for resonances. Now, here there are a couple of resonances that we observe when we say, for example, we say that we observe the Higgs. We didn't see a Higgs particle or a track that is left by the Higgs particle. We just looked at a scattering process in which the initial states are just 2 particles, 2 protons, that is the initial state. And the final state is, well, depends on your picture. Here there are 2, 1. The final state of this blue line is basically a Z boson and 2 Z bosons, let's say. That is what we observed. We never saw a Higgs directly. But you see here in the scattering, from an initial state that we observed to a final state that we directly observed, there is this peak over here. This is what we interpret as the Higgs boson. So you see, if you also consider the theory, Higgs, if you just turn off all the interactions, it's a stable particle, but there are interactions. Higgs is not a stable particle. It is not an eigenstate of our Hamiltonian. So there's no way we can have an infinitely lived Higgs. So it is short-lived. It lives such a short time that we cannot even see any track of it. But still we can infer that there is this Higgs boson that if we turn off the interactions, it would become stable looking at this peak over here. This peak is exactly the peak over here is exactly the idea that we have over here. Now here, this is one resonance we have. If I shift this axis, this is another resonance we have over here. But just note one thing. The higher the resonance, the broader it gets. This is not such a sharp peak as in the previous one. It is wider. And if you go to the third one, there is this bump over here which is barely visible. For it to become a very pronounced peak, you have to take lambda to be much larger. Now let's try to see this. So this is we are looking for states for values of k, complex values of k, for which this e to power 2i delta L minus 1 over 2i diverges. That is what we are looking for. let's see if we can find some approximate analytical expressions of it, where the pole is. So we are identifying this pole by as the bound state energies, as resonances, which would have become stable in the limit as lambda goes to infinity. But let's see if this is justified. Now what we have here is, okay, so e to power 2i delta L0 is b over c, b times e to power minus 2i k over c minus 1 over 2i, or b times e to power minus 2i k minus c over 2i c. Or let me rewrite this in this form, b over lambda tilde e to power minus 2i k minus c over lambda tilde over 2i c over lambda tilde. Now the reason why I divided by lambda tilde is that if you look at the expressions for b and c, they just diverge with as lambda tilde goes to 0. Now what we are interested in is, at least we know the solution, that if lambda tilde is infinite, we should have bound states. But for lambda tilde finite but very large, we will have these very narrow resonances. And that is what we are trying to figure out. What are the k vectors for which c, in this case, c over lambda bar, lambda tilde, diverges as a function of 1 over lambda tilde. So we know that the poles, the position of the poles depend on lambda tilde. The larger the lambda tilde, the closer it is to the real axis, and the narrower the pole is. So basically, I'm looking for an expansion for k in terms of 1 over lambda tilde. So let's say that k, which makes c over lambda tilde equal to 0, can be written as, in a sense, I'm making a perturbative expansion, but this time my perturbation parameter will be 1 over lambda, not lambda. K is equal to k0 plus k1 over lambda tilde. I will also look for k2 over lambda tilde squared plus terms of the order of 1 over lambda tilde cubed. This is the equation I would like to solve. Again, just order by order, I will be try to solve it. So let's see what C was. C is this one. So I'm looking for, well, let me just substitute it. Sine k0 plus, let me just write k1 plus k2, keeping in mind that k1 contains 1 over lambda tilde, k2 contains 1 over lambda tilde squared. Minus, this is 1 over lambda tilde, because this is c over lambda tilde, plus well, let me just multiply it out, this plus I times cosine k0 plus k1 plus k2 over lambda tilde, and plus I times sine k0 plus k1 plus k2. This should be equal to 0 for the k I have. Now let me pick up the terms that are of the order of 1 over lambda tilde to the power 0. The first term is 1 over lambda tilde to the power 1. The second term is 1 over lambda tilde to the power 1. So the only term that has 1 over lambda tilde to the power 0 is the last one. And this gives me sine of k0. This should be equal to 0. So if lambda tilde is equal to 0, already from the scattering amplitudes, I have these poles when k is equal to k0, which is equal to n pi. So this is the 0th order solution. This is the one we already had. Now, of course, lambda tilde is not infinity, or 1 over lambda tilde is not 0. We have corrections to this one. Let's try to calculate the corrections. The terms of the order of 1 over lambda tilde. Okay, from the first term, I have sine of k0. From the second term, I have I over lambda tilde cosine of k0. This has terms, I'm already taking 1 over lambda tilde. And plus I sine of k0 plus k1. This should be equal to 0. Now, of course, just keep in mind that in all these terms, I should only keep the coefficient of 1 over lambda tilde. Let me write these lambda tildes explicitly here. Now, k0 is n pi. This is n pi. This is n pi. Cosine n pi is just minus 1 to the power n. Sine n pi is 0. So I times minus 1 to the power n pi over lambda tilde plus I times, well, if you have an angle and add n pi to it, the sign just add pi to it, sign changes sign. So this is also minus 1 to the n times sine k1, and k1 is of the order of 1 over lambda tilde. So I can just expand sine of k1, keeping only the first term. This should be equal to 0. Minus 1 to the n's I can cancel. These ones I can cancel. So k1, the first correction is nothing but minus 1 over lambda tilde. So this basically tells me that the pole shifts to smaller values. Kn, remember k, n is k0, which is n pi, minus 1 over lambda tilde. If lambda tilde is finite, the poles should be at smaller values of kn, not at n pi. And that was what we had actually observed. So the pole was shifted to smaller values. So for example, if you look at, let me take it a smaller value. There should have been a pole when m is equal to exactly 3, right here. But it's shifted to smaller values because of finite lambda. And the shift is let's say, how much? It's shifted something like by 0.1. Well, 0.1 is 1 over 14, approximately. Let's see, let's go to the other ones. We should have a pole at 4. It is also shifted by more or less the same amount. So that is what basically our prediction is telling. For large values of lambda tilde, but not necessarily infinite, the poles, the real part of the poles, there's no imaginary part yet, the real parts of the poles are shifted to lower values of k, to lower than n pi. The shift is the same for all states. That was the prediction, and that is what we seem to be observing also numerically. Now let's look at the second pole. The terms of the order of 1 over lambda tilde squared. Let me just write the equation using the things that we already know. 1 over lambda tilde sine of n pi minus 1 over lambda tilde plus k2 plus I over lambda tilde times cosine of n pi minus 1 over lambda tilde plus k2 and plus I sine n pi minus 1 over lambda tilde plus k2. This should be equal to 0 up to terms containing 1 over lambda cubed. Because on the left-hand side we have thrown away all terms that are of the order of 1 over lambda cubed. So it need not be 0, but if it differs from 0, the difference will be terms that contain 1 over lambda cubed. So let's see, this is 1 over lambda tilde minus 1 to the n sine of minus 1 over lambda tilde plus k2 plus I over lambda tilde minus 1 to the n cosine of minus 1 over lambda tilde plus k2 By the way, there is one thing I forgot. One thing I made a mistake. So this is a over, in the cosine, no problem, but the sine contains 1 over k, which I forgot. So let's try to correct it. Well, the first term doesn't change, so it's just sine k0 over k0. Sine k0 over k0 should be 0. That's the only change. Now in the second one here I have 1 over k0 plus k1. This should be 0. So the first term is the same, the second term doesn't change, and now this is 0 anyway. This remains, so this one I have to multiply it by, or let's say divide by k0, and 1 plus k1 over k0 to the power minus 1. This should be equal to 0. And let's see, 1 over lambda tilde plus k1. Well, nothing changes actually. K0 is n pi. One minus, well, k1 over k0. So this basically, okay, this is higher order, which we are ignoring at this level. So this tells me k1 is actually minus n pi. So this is n pi 1 minus 1 over lambda tilde. So the shift should be increasing. Probably we didn't see it because we were just looking at small changes in n. Now here, let us also add k0 plus k1, or n pi times 1 minus lambda tilde plus k2. Okay, so this is the equation that we need to solve. And let me just rewrite it. Minus 1 to the n, 1 over lambda tilde. Now what remains, these are just small numbers, so we can expand the Taylor expansion, and we need to keep terms up to the order lambda. Well, we already have the 1 over lambda tilde. We only need the terms up to 1 over lambda tilde in the expansion of the sign, which is just minus 1 over lambda tilde. K2 is 1 over lambda tilde squared, so it doesn't contribute. It contributes at a higher order. Now, when we look at the cosine, it's again minus 1 to the n due to this n pi. And then we have I over lambda tilde. Well, the argument is of the order of 1 over lambda tilde. So if you expand the cosine, you have the 1 minus argument squared. But the argument squared is of the order of 1 over lambda tilde squared. I already have a 1 over lambda tilde. So up to terms containing 1 over lambda tilde cubed, I can just replace cosine by 1. And then plus, here I also have an I, plus I minus 1 to the n. And sine, let's see, the expansion of sine just brings me 1 over lambda tilde plus K2. The next term is the argument cube, which will contain terms smaller than 1 over lambda tilde squared, so I can just ignore them. And then, of course, I have this term, so let's write it in the form 1 over n pi times 1 minus 1 over lambda tilde plus K2 over n pi to the power minus 1. This should be 0, or of the order of 1 over lambda tilde cubed. Okay, this is the equation. And let's proceed further. Now, minus 1 to the n's, they are everywhere. So we have minus 1 over lambda tilde squared minus, well, this term is 1 over lambda tilde. It will cancel the other 1 over lambda tilde term, so I'm not writing it down. This I over here. In this term and in this term, both of those two terms contain an I. The I was already there from the beginning. You see, this I multiplies these two factors. I just opened up that parentheses. Now, anyway, we can just proceed. Now, let me not write down explicitly. The thing is, K2 will be imaginary. You see, the first term is real. The second terms have this factor I, and when you make these expansions, etc., K2 will also have these factors of I. So there's a real term plus I times terms containing K2. So K2 has to be pure imaginary. And if you just do the calculation, you will see that Kn is n pi 1 minus 1 over lambda tilde plus I n pi over lambda tilde squared. Plus, of course, we have other corrections. Let's look at the energy. Epsilon n is equal to Kn squared. So this is equal to let's look at the imaginary part of epsilon n. This will be proportional to, let's say, 2 n pi cubed over lambda tilde squared. Now, this 1 over lambda tilde, we said that, okay, if lambda tilde is infinite, there is no tunneling. There is no coupling, there is no decay. So if you start with this compact state, bounded state, then it just stays bounded. There is no way it will go away. But if 1 over lambda is non-zero, then there is a finite probability that this will tunnel. And the tunneling amplitude will be, naively you would expect the tunneling amplitude to be proportional to 1 over lambda. And so the tunneling probability will be 1 over lambda tilde squared. So this is our tunneling probability. The lifetime should be proportional to the inverse tunneling probability. So the lifetime will be proportional to lambda tilde squared itself. Now, in fact, this is actually what we call the gamma over 2. And gamma tau being the lifetime. So we can now identify also how long this state will live by just looking at the imaginary part of this energy. Now, how do we identify the imaginary part of energy with lifetime and the real part with the real mass? Well, let me just review one of the arguments we had before. Now, let's just imagine we have many particles sitting there in our potential well, and let's say they are all at the same state. So the number of the particles is given by nothing but the wave function squared. Wave function is not normalized to 1, but n. And we also know that the number of particles in my shell will get smaller and smaller. And this rate is how fast the numbers are decreasing per unit particle. But this is nothing but the tunneling probability. This should be equal to what we call, this should be just some number, some fixed number gamma you can identify as tunneling probability. So this tells me that dN by dt should be equal to minus gamma n, or n as a function of time should be n at t equal to 0, e to power minus gamma over 2 times t. But you see, the n is kind of my wave function. And the time evolution of my wave function will be given by psi x, if it's an eigenstate or an almost eigenstate at t equal to 0, e to power minus I e times t. But at the same time, it should also have this imaginary dependence. So this is if it is almost stationary, then the only time dependence is due to this e. But now there is also this tunneling probability. Even if I create a particle in a given state, the number of particles in my region is decaying away. So that I can just model as a non-unitary evolution of my wave function. So I can just say that psi of x and t is equal to the wave function at t equal to 0, e to power minus I e of t minus gamma over 2 times t. So this here I have a gamma. So if the tunneling probability is 0, then gamma is 0. And gamma is 0, I recover this one. If gamma is non-zero but very small, then it is almost given by this one over here, almost. But there is also this factor. So this is what we call the resonance. And so we can also write this as psi x t is equal to 0, e to power minus I times t, e minus I gamma over 2. So this is why the real part, this is what we call the energy. Let's say EC, ER. Real part of the resonant energy is nothing but the energy of my bound state, or object that is confined state, let's say. And the imaginary part is nothing but the tunneling probability with a minus sign. So here we have both of them. And And if you just take the imaginary part, the tunneling probability, we already expect it to be 1 over lambda squared, and it actually turns out to be proportional to 1 over lambda squared. So it kind of makes sense. We also know that the real part of the energy, or real part of the momentum, is if lambda tilde is very large, that is, if gamma is small enough, the real part does actually correspond to the confined object's energies, with a very slight shift due to 1 over lambda tilde for large lambda tilde. Now, of course, these are kind of pathological examples in the sense that we never have this potential well in the shape of a square, or we never get this Dirac delta potentials. But they are basically some prototypes, some approximations to the potentials of this form. Let's say we can imagine such potentials. This is V of R as a function of R. Now, this is not an unrealistic potential. For example, if you would like to model the nuclei, this is one way you can do the alpha decay, for example. What we say is the alpha particle is kind of a resonant state trapped inside the nuclei, which has a finite tunneling probability throughout the nuclear force, nuclear potential. So if you have such a potential, you would expect some bound states here that will be oscillating and decaying out of it, and some resonant states over here, which they can live for a long time. I mean, if you just consider the alpha decay, there are some isotopes that live ages. Eventually they decay. So you can have resonant states that eventually decay, but they live such a long time that you can identify it as a new kind of state. So for such a potential also, the two problems that we studied is kind of these two extremes. I mean, this you can just model by the sum of the two potentials we had studied. This one and a Dirac delta. Well, this will be a very simplistic model, but it still captures some of the properties. There will be some bound states, not many, just a few, depending on your parameters, and there will be some resonant states, not infinitely many. In the Dirac delta example, we have infinitely many resonances, but nevertheless, for those infinitely many resonances, even for those infinitely many resonances, physically the relevant ones are the ones that can be observed. So for example, even if lambda is 50, okay, the third resonance we can observe, the fifth one, yes, sixth one, yes, seventh, yeah, 7, 8, there's no sign of the resonance anymore. So even if we have infinitely many bound states in the limit when lambda goes to infinity, some of them just live so short that you cannot really claim that they are formed in the experiments. Now, any questions on these?
So you can say that, for example, alpha particles cycle out of the way like that, but for example, how does, I don't know, say a pion decay? Because in that case, like 2 quarks decay into 2 photons.
But you see, forget about the particle content. Just look at the states. So what's the thing is, you have these one state which can make a transition to another state. Will it live long enough, your initial state? Will it live long enough? Now, in this example, the initial state that we are looking at whether it will live long enough or not are the states that are bounded inside our shell. In the case of the pion, it's the pion. The other state that our initial state can make a transition into is in the shell problem is the states that go to infinity. In the pion case, it's the 2 photons. So looking in terms of only the states rather than looking at the details, those 2 problems are identical. So you have one state which has a small which has a probability of tunneling or transitioning into another state. But this transition probability or the amplitude, if this transition amplitude is small, then that initial state you can identify as a resonance. It will have a finite lifetime, but you can still give it a well-defined energy. If you think in terms of these terms, then the pion decaying into 2 photons and this particle confined in your shell going out of the shell is identical. And you can even, although we are looking at 1 particle and 1 potential, I mean, this is the same thing as 2 particles interacting through a central potential. So if you have this compact object, that just means those 2 particles can just form a state which is very localized in space, but it has a finite lifetime. Eventually, they will just dissociate. Questions? Now this will be kind of our last lecture on scattering. And next week I will be starting the path integrals. That will be just a different formulation of quantum mechanics. Now you have already seen 2 formulations. One is the Schrödinger equation. One, we had seen the Lippmann-Schwinger equation. If you remember, we converted the Schrödinger equation to an integral equation. That equation is called the Lippmann-Schwinger. That's just an alternative formulation of the quantum mechanics. And now there will be the third one, which is path integrals. They are all equivalent to each other. If you can solve one, you can solve all the other one. But in certain treatments, some of them will be more intuitive than the other ones, etc. So see you on Tuesday.